Hey guys, thanks for checking this out. I want to share with you guys my stable chaos model. You can find it on GitHub, Big Stick Studio /stable chaos. This is not on our website yet. This is something I'm still kind of developing. The model has been a concept that I have believed in for a long time. And this is in response to Purdue's p-bit. So the concept with a p-bit is that there is this probability bit, that there is a fluctuation between 0 and 1 that we can determine deterministically. A normal bit is 0 or 1, and then a qubit is something that has a superposition of 0 or 1, which means it has the potential to be either. I saw this, and there's a lot more to this. There's a lot you can do with this. But as soon as I saw this, I knew that it was incomplete because there is a theory that I've had for a long time, and that is that things exist in nature non-statically, non-binary, in their own opposition. And you could use a lot of different examples, but where something might be true but might not be correct, or might be correct but might not be true. And things often exist this way, not only in our life, but in nature, as existing between states, like the concept of chaos and stability. They're not mutually exclusive. And so when I saw this, I decided to try to program it in a few lines of code. I was able to do that with Python and Pygame and a few hundred lines of code, and that's what I'll show you. But the concept here is that A and B should be polar opposites, and that they also would share characteristics. So a interim state of A, B would be this superposition of these polar opposites, and then it would also need its own inverse, and therefore A shares characteristics of not B and A. And the interesting thing about this model is that it's the opposition that creates stability. So if B was 1 and A was 0, then that would be a stable system. But it's when A tries to be like both of its opposing neighbors that we see chaos introduced. And that's what makes this a stable model. So the rules are simple. A single node in the system will try to maintain attribution towards one of its neighbors, and the inverse towards its opposing neighbor, while attempting to maintain an opposing movement to its own opposite. So it's going to try to be like and dislike its own opposites at the same time. I don't know how else to explain it. There are 2 degrees of freedom, plus or minus 1. We just recently changed this to be floating point values so that we can have an infinite degree of freedom between these 2 points. Right now we're using basically a tenth. It's not exactly a tenth. It could be scaled down to infinitesimally I can't say that word. Infinitely smaller. Meaning that each node has a superposition of A, B, not A or not B. We were initially changing from black and white and interpolating between blue and red. And you can see here where the system is going to try to oppose itself now. Like this would be able to stay this way, but it can't. So it's going to try to oppose itself while being like its neighbors simultaneously. We are achieving this by creating a copy of the comparison. So when we where is it at? When we calculate new node values, we actually make a copy, and then we update these values, append that value into the new copy, and then make a complete shift all simultaneously. This actually could be improved upon with double precision iteration and doing this at a node per node level. But this is sufficient for this example. There's no need to have something that precise. But yeah, this system has between 6,000 and 300,000 potential states, depending on if you calculate 4 to the power of 9 or 9 to the power of 4. Now, if we get into the technical details of this, not super technical, but just overall view of how this thing works, we have the ability to add a fraction of a decimal, subtract, and then we also repel. So in the repel state, we do the opposite of whatever the other is doing no matter what. The exception to this rule is that if we are, so first case is if we have the opposite, we do the opposite no matter what, because that's where the stability in the system comes from. The only other factor is if we have some randomness that we calculate every time, which is just 1 or -1, or a value in between, which is 0. So if we have 0, we just do nothing. So if we have both values being above 0 or 1, then we actually want to do the inverse here. So if A and B are, actually this is kind of pointless conditional here, we can just remove this. Because if they're both above 1, there's no point in checking it again. It will never be less than or greater than 1. So yeah, if we have a double positive, we want to attempt to move away from our neighbor. If we have a double negative, we want to attempt to overtake our neighbor. Really, this could say undertake, but nevertheless, the other condition here is our left neighbor and our right neighbor is also inverse in their direction, and we could do away with this as well. There's a lot of different ways you could construct this system. You could even randomly construct the rules of this system if you wanted to introduce more chaos. As I said, this rule of opposition will always attempt to create stability, and that in the likeness of its neighbors, it creates its own opposition. And we see that here. If we have a mix of positive and negative, we want to attempt to be like our neighbor in one way or another. And yeah, so these are just the rules. We plus or minus depending on what random decision we decided to make. So let me just do away with the code and actually show you. The only other factor that I would like to outline here that we've added is that we added a high level circle that encompasses the entire state, and it was flickering really hard to look at, so we store the previous red, green, blue values, and we are finding the min and max. I was averaging all of them, but then that also adds, it just gets hard to look at. The min and max are sufficient because if our minimum is white and our maximum is white, we're going to end up with white. But nevertheless, let me just go ahead and show you. So here it is. The other thing I did was I scaled it to average it down a little bit so that way the colors aren't muddying up. But you can see here, the system is going to try to like stabilize in polar opposites. You can see red and blue obviously trying to emerge, and we will see the state continue to shift. It can never form true polar stability. It will always be shifting in and out of its own states. You can see white eventually will change to different positions. Nothing will ever turn black, but you can see here there is stability. And then it will become its own inverse through the opposition of its neighbors. And yeah, that's basically the concept. And I was able to prove that this exists in a couple hundred lines of code. You're free to check this out. This is, I guess what you could call an open source project. It's really just a theory that I think I've proved. And I don't really know what to do with it beyond this. I'm open to suggestions, ideas, love to hear from people. Feel free to reach out in the comments. You can comment on GitHub, and you can just reach out. I will find ways to communicate with people if they want to connect. We are working on building up our websites and our community engagement and opportunities for people to become a part of this. One thing I would like to state is that we have this running at 30 frames per second. You can speed it up to 100, and you could also shift the state here a magnitude higher, and you will see this thing really be chaotic. We have to slow it down for it to be noticeable. And I just could imagine how fast this thing could work if it was running at 5 gigahertz on my GPU, or even on a quantum computer. It would be so fast that we wouldn't even be able to see the changes shifting, or it would look completely stable while it's in this extreme state of what looks like chaos. But nevertheless, like I said, this thing is hard to look at in that level. We could also slow this thing down even more. We could add another degree of this is at 100 frames a second. These values will shift a lot slower. Still hard to look at. We could go back to where we were at and go to 10 frames a second. And even then, it's arguably more smoother transitioning. Enough changes to actually observe the changes that are happening. But yeah, I could keep going on about this, but really there's not much more to it. I'd love to hear you guys' thoughts, feedback, opinions, insights, and yeah, I mean, I don't even know what to do with this thing. So really need some community feedback or some ideas of what to do with this thing, or maybe I'll just leave it here. But yeah, hopefully this is useful, helpful, insightful, and not a complete waste of time. But yeah, thanks for watching, thanks for tuning in, thank you for your time, and hit me up. Peace.